In this circle diagram, there is a 3-phase, 6-pole, 50 Hz, 400 volt star connected induction motor. So here the no load test is given. So for initial calculations, I naught is equal to 10 amps. So this is the no load current at rated voltage. And here there is no power factor given in order to check the phi naught angle. So we have a formula root 3 VL IL cos phi. So we have the no load power, that is 1400 watt. 1400 divided by root 3 into VLIL, that is 400 into 10 amps, that is P naught divided by root 3 into VLIL is equal to cos phi naught. So phi naught is equal to 1400 cos inverse of 1400 divided by root 3 into 400 into 10, which is almost equal to 78.34 degrees. Moving on to short circuit test or block rotor test. So here the current is 55 amps at 200 volts. So we have to check what is the current, the block rotor current at 400 volts. So if 200 volt 55 amps, then at 400 volt what is the current? We are doing this because we need to bring all the values to the rated value of voltage. So if at 255 amps at 400, what is the current? Which is equal to 110 amps, that is ISC, short circuit current at rated voltage. Now we have to find what is the power, short circuit power at rated voltage. So here they have given 7000 watts at 200 volts. So what is the power at 400 volts? That will be, the formula is WSN is equal to WSC into V rated divided by V short circuit whole square. It will be 7000 into 400 divided by 200 whole square, which is equal to 28,000 watts. So we have got short circuit current, short circuit power at rated voltage. Now we have to find short circuit angle, phi SC. So it will be cos inverse of the power at rated voltage, that is 28,000, the power at rated voltage, divided by root 3 VL, that is 400, because we are calculating everything at rated voltage, into current at rated voltage is 110 amps. So which is equal to phi SC is equal to 68.44 degrees. Here the no load current is 10 amps and the short circuit current is 110 amps. So let us take one division. Since x-axis is current scale and y-axis is voltage scale, on x-axis 1 centimeter is equal to 5 amps. Let us take current scale as 1 centimeter is equal to 5 amps. So it will be 5, 10, 15, 25, 30, 35, 40, 45, 50, 55, 60, 75, 80, 85, 90, 95, 100. Now drawing no load phasor. Here the no load current is 10 amps. So according to our current scale, that is 1 centimeter is equal to 5 amps, we will have to draw 2 centimeters in order to do 10 amps. So the angle of that current is 78.34. So placing the protractor on the origin with 0 on the voltage axis, draw a point at 78.3 degrees. Now from this point, draw a line of 2 centimeters from the origin O. From the origin O, draw a line of 2 centimeters passing to the point whatever we marked. So name this point as O dash. So after that we have to draw the short circuit current 110 amps at 68.44 degrees. So placing point on origin O with 0 on y-axis, the angle is 68.44. Now since it is 110 amps, it will be, if 1 centimeter 5 amps, how much is 110? So it will be 110 divided by 5, which is equal to 22 centimeters. So from the point O passing to the point which will be marked, that is at 66 degree, draw a line of 22 centimeters. Mark this point as A. Now from point A, draw a line downwards which is parallel to our y-axis. So it is getting contact with the x-axis at point D. Now from point O dash, from the point O dash, draw a line perpendicular to our y-axis which is parallel to our x-axis. So here there is 4 mm, almost 5 mm. Here also it will be almost 5 mm, both the sides. So this is 5 mm. So the point where these both lines are intersecting, let us consider it as F. Also draw a line from O dash to A. We have to intersect in order to get our output line. So this is our output line. We have to draw now a perpendicular bisector to O dash A. So here for this O dash A, we have to draw a perpendicular bisector. From O dash, draw arc. And from A, draw, join the arcs. So in order to draw the perpendicular bisector, which should pass through our x-axis as well as the upper line, as well as little bit longer in order to pass through the circle. In case if you are not able to draw the arc and the perpendicular bisector with the protractor, then just use the scale and check what is the length of O dash A. So here it is 20 centimeter. So what you have to do, at point we have to, if it is 20 centimeter, you have to make half of that, that is 10 centimeter. So at point 10 centimeter, just make a mark on this line, make a mark. After that, draw a line perpendicular to our output line, that is O dash A. We have to draw from that point, we have to draw a perpendicular line. So by this also we can do a perpendicular bisector. Now take the compass. Before that, we'll mark this point as C, where it intersects the upper line, that is C. So from point C and keeping the pencil on O dash, draw a circle. So which will pass through our point A. Here AD gives us the total losses at block rotor condition. So FD is our stay loss, that is constant loss which does not change. Now AF is our rotor and stator copper losses. So here in question they are given as stator has a loss of at standstill, stator has a loss of 60% of total copper loss. Out of this total copper loss, out of this AF, 60% is stator copper loss and the rest 40% is rotor copper loss. So from down the value is of stator, then up will be the rotor. So 60% is stator, then 40% is rotor. So AF is almost equal to 7.5 centimeters. So 100% is 7.5 centimeters. 100% of copper loss is 7.5 centimeters. Then 60% is how much? That will be 60 into 7.5 divided by 100, which is almost equal to 4.5 centimeter. So our stator copper loss is 4.5 centimeter out of 7 centimeters. 7 out of 7.5 centimeters. So we will mark a point. Since stator copper loss is at the bottom, it will be 4.5 centimeters. 4.5 centimeters. Let us mark this point as E. So from this point we have to draw a line towards O dash, which is our torque line. If this stator and rotor copper losses are not given, we have to consider that stator copper loss is 50%, rotor copper loss is 50%. So we have to measure AF and make half of that and mark the point as E. So if it was 7.5, for in this example, if stator copper loss and rotor copper loss is not given and the value is 7.5 divided by 2, it will be almost equal to 3.75. So mark it on 3.75 and draw the line of torque. So here, since it is given, we have to follow according to that. And again here it is given that the full load current is 30 amps. So sometimes either they will have the output given at this area, or they will give us the full load current. So if output is given, we have to draw a line above as a dash. If this current, that is full load current, is given, then we have to mark from O, we have to make an arc of 30 amps. So how to do that arc? We have taken current scale as 5 amps. So if 5 amps is 1 centimeter, then 30 amps is equal to how much? It will be 30 by 5, which is 6 centimeter. So we have to draw a arc of 6 centimeters. Measure 6 centimeters, and from O cut a arc on our circle, so that this line, that is this point, is P, and mark it as, we have to draw a line. So this is the current that is given, we have drawn. So from that point, draw a line straight downwards till the x-axis. So here we'll get the rotor copper loss, all the losses and the output. So here we'll mark those points. The the line intersecting the output line, this point is taken as Q. The bottom in between the line, that is torque line, intersecting the P line, which is coming downwards, that is R, and below that, yes, let us mark T as the bottom down, this point. So these four points are marked: Q, R, S, and T. Now here it is, we have drawn a perpendicular to our output line. So this is the point. At this point, mark it as M and draw a line downwards up to the output line. Since we have drawn a line perpendicular to the output line, which is passing through point C and intersecting the circle, from there draw a line straight downwards till the output line. So we'll mark it as N. Now let us draw a line passing through point C, which is perpendicular to our torque line. And passing through point C. Bring it till the torque line. It is perpendicular to, bring it till the bottom, till point C, which is perpendicular to our torque line. So this point is J. From point J, bring a line downwards until the torque line. So this point is K. So here this length gives us the maximum output, and this length, since it is linking perpendicular to the output line and is linking to the output line from the circle, so this gives us the maximum output. And the other line, which is perpendicular to our torque line and is linking our torque line from the circle, JK, gives us the torque value, the maximum torque value. They have given efficiency, speed, torque at full load. So all the values the full load values are calculated at this region. And in question they have given us to find out uh, maximum power input, maximum power output, maximum torque. So here we found out maximum power output from the output line, whatever line we did, maximum power output we did, then maximum torque output we did. Now maximum power input, whatever we give to the motor, that we have to do by drawing a line from point C. From point C, draw a line straight upwards, which is line which is perpendicular to our x-axis. Straight upwards we have to draw until the x-axis bottom, till the bottom, and mark the point where it intersects the x-axis as R and the top as R dash. So this is our maximum power input to the motor. Here, since we have to find slip at maximum torque, so the formula for slip is rotor copper loss divided by total rotor input. So the rotor copper loss divided by total rotor input. So here we are finding for slip at maximum torque. So maximum value, maximum torque output is Jk. Here to find slip at maximum torque, we have to use the line Jk and mark a point W on this point on the output line. So here to find slip at maximum torque, we have to divide the length of Wk by Jk. Because the formula is rotor copper loss divided by total rotor input. So here this is the above the output line, it is Jw, that is the output. Output plus loss will be the total rotor input. So it will be our total rotor input will be Jk, and rotor copper loss, that is this is the copper loss length. So here Wk is the copper loss at this line. So it will be Wk divided by Jk, the slip at maximum torque. We have to mark the angle, that is no load current line, that is OO dash, that will be phi naught. The other line will be short circuit current, that is phi SC, and here the PO line, that will be phi. This will be the phase angle at full load. This is the full load values. So now in order to find the full load efficiencies, full load values, that will be they have asked slip at full load. So that will be as we told, slip formula is rotor copper loss divided by total motor in the rotor input. That will be rotor copper loss, that is QR. Here QR is almost 2 mm. QR is almost 2 mm. That will be QR slip. The formula is QR divided by PR, rotor copper loss divided by rotor input. So it will be QR, that is almost 2 mm, that will be 0.2 centimeter divided by PR. PR means the total rotor input, the loss plus the output, that is almost 5 centimeter, that is 4.5. So this will be 0.04 slip at full load. Then they have asked power output at full load. So power output at full load, the formula is output power. It is PQ into power scale. Now we have to find the power scale. We have not found the power scale yet. In order to find the power scale, we have to calculate what is the value of A to D. This is all the total power input at block rotor condition. The total power input at block rotor. So it is almost 8 centimeter. So we have calculated what is the power at block rotor condition. At block rotor condition, we have calculated the power. So to find the power scale, we have got that AD is 8 centimeter. So 8 centimeter is 28,000. So that is the total power at block rotor test. Then what is 1 centimeter? The power for 1 centimeter. So it is equal to 3500. So power scale which is equal to 3500. This is 3500 watts for 1 centimeter. So we have got our power scale, that is 3500. So here the the input power will be here we are finding power output at full load. So the output power is PQ. That is almost equal to 4.1 centimeter. So it will be 4.1 into the power scale. What we got, power scale is 3500 in this case, 3500. So it will be 14,350 watts. Now these are the formulas for the calculation part at the final. If the diagram is done with these notations, so you can take a screenshot of this. So here these are the formulas for all the calculations whatever is required in the problem. So you can take the power scale, that is 3500 in this problem, and just measure all these values and multiply according to that. Here the torque will be in synchronous watts, then the rest all the outputs will be in terms of watts, and efficiency in terms of percentage if multiplied by 100. Here there are extra formulas in this problem, that is maximum power input and slip for maximum torque. Now to find power factor, that is cos phi at full load. So we have to measure this angle after drawing that whatever we drew OP line. We have to measure the angle of that with respect to our voltage axis, our y-axis. We have to check the angle. So here it is 30 degree. So cos power factor PF is equal to, at power factor at full load, is equal to cos of 30 degree. So cos 30 is equal to 0.866. This is the power factor to calculate. These are all the formulas, and this is the diagram. So this respective of formulas, the whatever notation is given there, you can just measure those and multiply with the power scale or the current scale. So here the current scale is 5 amps. Apart from this, they have asked speed at full load current. So here to find full load current, we will be finding, first we'll be finding our slip at full load. That will be this formula, that is rotor copper loss divided by total rotor input, that will be Q R, this value, divided by P R. So we got the slip, that is 0.04 in this calculation. Now they have given in question that it is a 6 pole 50 hertz. So there is a formula for synchronous, to find the synchronous speed. There is a formula, that is Ns is equal to 120 F by P, where F is frequency and P is number of poles. It will be 120 into 50 divided by 6. So it will be 1000 RPM. So we have got synchronous speed. Now to check the actual speed at full load, the formula is N is equal to 1 minus S, where S is slip, into Ns, which is equal to slip we have found, that is 0.04. That will be 1 minus 0.04 into Ns, that is 1000, which is equal to 1 minus 0.04 into 1000, which is 960 RPM. So the speed is also calculated by this formula, where we find slip at maximum load, full load, because they have asked speed at full load. So we have to check what is the slip at full load. On that we have to apply this formula, where synchronous speed is calculated depending upon the frequency and poles, and normal speed at full load is calculated.